Welcome, Professor Giulia. You need to unmute your mic.
Sorry, good afternoon, everyone.
Hello, Professor Giulia.
Hi,
Professor
nice to meet you.
Your voice is little low.
I'm very much thankful you accepted our invitation.
Hello.
And
You could hear me?
You talk today to our students.
We can't hear you.
So Dr. Anjani will formally welcome you.
We can't hear you, Professor Giulia.
No, I was listening to the dean of the school.
Yeah. Please go ahead.
Yeah. Thank you very much for your. Thank you very much for your kind invitation.
Thank you very much for joining today. Anjani, you can proceed.
Okay. We will wait for the participants to join, and maybe we'll start in 5 minutes.
Okay, but at 10 sharp, I have another talk, but I think we can arrange.
Okay. Thank you. Okay. We will start. Participants will keep on joining. Yeah. So good afternoon, everyone. I, Dr. Anjani Nagvekar, on behalf of 2D-SAGE organizing team, welcome you all for this third webinar of the series. We started this webinar series with an aim to provide a platform for the young minds and researchers to interact with the eminent scientists in this field of semiconductors, and to apprise them with the trending and emerging two-dimensional semiconductors in energy applications, and especially we are focusing the photovoltaics. So today we have among us Professor Giulia Grancini. To introduce briefly, Giulia Grancini is Associate Professor at Chemistry Department of University of Pavia and leading the PV²2 team and the ERC project High Nano for developing advanced hybrid perovskite solar cells. She obtained her PhD in physics from Politecnico di Milano in 2012 and worked as a postdoc researcher at IIT in Milano. From 2015 to 2019, she joined the EPFL, awarded by Swiss National Science Foundation with the Ambition Energy Grant. She is currently the Italian Universal Scientific Education and Research Network Ambassador and a board member of the Young Academy of Europe. Since 2019, she has been among the highly cited scientists from Web of Science with H index of 50 and more than 20,000 citations. She has been recently appointed Cavalier della Repubblica for scientific merits by the Italian President Sergio Mattarella. She has been listed among the world top scientists in 2019, 2020, and 2021. So thank you, Professor Julia, for accepting our invitation, and we are honored to have you as a speaker today. Kindly excuse me if I misspelled.
No, you pronounced everything in a perfect Italian accent. So thank you very much for the invitation, and sorry for the timing. I have a very intense day today because I start with the lecture with my students. So I'm sorry, but at 10 I really have to leave. So it's a great pleasure for me to be here with you, even if remotely. So thank you very much for thinking of me for this talk. It's a real honor. I share my screen. Can I? Okay.
Okay. So please take over.
Here.
Yeah.
Allow. Okay. Can you see my screen?
Yes. Yeah. It is visible.
Okay. Maybe like this is better. Yes. Okay. So let's go straight to the point. My work relates, yes, in part on 2D novel materials for a big challenge, which is the challenge for solar energy revolution. So nowadays we know that the silicon dominates the market. However, it has a very technologically intensive and energy consuming technology. So the challenge for tomorrow is to go towards modern needs of energy, which integrate a low-cost, adaptable and portable concept of solar energy. So the question is, how can science and innovation bring us closer to this goal? From the past, this is the NRL graph that maybe you know very well, with reporting the solar cell efficiency of all the technologies over the years. You can see that in the very recent years, in the last 10, 12 years, I would say, there has been developed a new technology which really emerged and upon 10 years of research reached efficiency values comparable to standard technologies. They are the so-called hybrid perovskites. So this will be the topic of my talk. Hybrid perovskites have been really skyrocketing the efficiency in such a short time of research, which is something unprecedented compared to the development of any other existing solar technologies. Hybrid perovskites are an ABX3 network of crystalline materials, where A is the organic cation, usually methylammonium for magnesium, B the metal, and X the halide, like bromide, chloride, B usually is lead. So this is hybrid, the so-called three-dimensional hybrid perovskites with unique properties in terms of efficient optical absorption, efficient charge diffusion, and high charge mobility that are really incredible properties to enable this material to reach such a high efficiency in a short time. However, there is a problem for these materials, and the current challenge for this technology is the stability. So we know very well that to go towards a commercial solution, we need to simultaneously satisfy three pillars: low cost, high efficiency, but also high stability. Excuse me. High stability in terms of durability of the material. And this is the problem now. The hybrid perovskites, when exposed to water, humidity, heat, or UV light, degrade undergoing an irreversible degradation of the material in a way that the 3D perovskite from black turns yellow, which is the color of the lead iodide, which is the precursor of the materials. So the 3D structure collapses with even potential release of toxic element. So this is nowadays a big barrier for the commercialization. So my group is working on a different class of materials which are called 2D perovskites, which you can obtain by simply imagining to cut the 3D perovskites along the inorganic planes. So you have a single inorganic layers which are spaced by large organic cations, ending up with this formulation. Why are they interesting? They are interesting because with respect to the 3D perovskites, you see that they do not show any visible degradation upon exposure to water and humidity. So the stability here reported with respect, that is basically the efficiency under time, is much enhanced with respect to the 3D. So of course, this is a very interesting material which can be used in, to stabilize the perovskite solar cells. So the concept that we developed is to create a new synergy between the 3D and the 2D to create a new hybrid framework combining the efficiency of the 3D and the stability of the 2D for new functional, stable, and efficient 3D 2D solar cells. There are many different ways of combining 2D and 3D perovskites together, and this has been under intense study in research in the last, I would say, 3 or 4 years. So when you take the two components, first thing you can do is you mix them together, like in a blend, like in an heterojunction, forming this mixed 2D, 3D perovskite. Or you can use a very tiny amount of 2D to just passivate the ring boundaries of the perovskite. Or alternatively, you can form the so-called layer-by-layer structure, where you have a 2D perovskite layer on top of the 3D. In particular, this layer-by-layer structure has been the one that was first developed in 2018. Here you can see some example of publications in an NIP configuration, where you have the 3D and then on the top the 2D perovskites. To form the 2D perovskites, you can choose the organic cations that can be phenyletilammonium, can be thiophene-based cations, fluorinated derivatives, fluorose 2D. So you can see that there is a very large library of 2D cations that can be used to improve, to form the 2D perovskites. With this layer-by-layer structure, the most interesting thing is how do you deposit the 2D on top without dissolving the 3D underneath? So first of all, the process. Well, the process, it's very simple. You create by a two-step deposition methods, first the 3D perovskite with an excess of lead iodide, and then you drop the you deposit the precursors, the organic cations of the 2D perovskites on top, which can react in situ with the excess of the lead iodide to form this very, very thin layer on top, you can see it here, of 2D perovskites. The 2D perovskites have a wider band gap with respect to the 3D, so that you see from PL, exciting from the top side, that the emission at 500 nanometer is a clear signature of the presence of the 2D perovskites. Overall, what is the role of this gradient structure? The 2D perovskite on top improves the water repellent character of the surface. You can see here by contact angle, which increases a lot. which in turn leads to an improved stability of this 3D 2D structure with respect to the only 3D. So basically, you are making your device more robust to water humidity, preventing the degradation of the 3D perovskites. Of course, to do that, you really need to optimize the interface structure, the processes, and the materials that you used. Here, I would like to present to you, I would like to present to you a recent work that is just submitted, where we used FAPI-based perovskites, which is nowadays the most efficient one, that we doped in the bulk with MACL, but importantly, we make a thin layer of 2D perovskites on top of it, following the strategy of 3D, 2D bilayers. So first of all, it's important to characterize the bulk material, and you see from XRD that you do have evidence of the formation of a stable perovskite phase, the alpha phase. But when you use this phenylethylammonium-based cation, which is this one, to form the 2D perovskites, you do have also another peak at lower angles, which are indicative of presence of the growth of this thin layer of 2D perovskites. Also, another evidence of it comes from TOF SIMS measurements, time of flight secondary ion mass spectrometer measurements, where you can see that the chlorine contact at the interface between the perovskite and the spiro increases when you have this phenylethylammonium chloride 2D-based 2D perovskite at the interface. So, you are creating this interface, and what is happening? Well, what is happening from a physical chemistry point of view is that when you map the photoluminescence signal of your combined 3D 2D system, there is a 5 times increase in the photoluminescence, and in particular in the photoluminescence quantum yield, showing also a very homogeneous distribution of the emission from the 2D perovskites. I told you at the beginning that the 2D perovskites emit around 500 nanometer, no? So this is at 800, the emission with the 2D perovskites, which increases a lot. And then here is the emission mapped at 500 nanometers, showing the emission of the 2D perovskites, which indicates a very homogeneous distribution. The take-home message here is that such an increase in the photoluminescence indicates a reduction of the non-radiative losses of trapping at the surface. In other words, it indicates surface passivation, which is really the key to improve the lifetime of the carriers. So you can see here by the photoluminescence lifetime, which is the key to improve the device VOC and the device performances. So with the addition of this 2D layer, the key message is that the 2D layer does not only improve the water hydrophobic, let's say the hydrophobic character of the surface, but it also improves dramatically by surface passivation, the surface quality, increasing the photoluminescence quantum yield, thus reducing the losses, which in turn leads to this improved VOC that we always see when we have the addition of this 2D layer on top of the 3D. This is very important because it's important, is an essential element of the added function of the 2D perovskite on top of the 3D. So what's the power of the 2D? Improve device robustness, but also performances, affecting the interface, suppressing interface recombination. But it's very important to simultaneously control the interface structure and properties. But the question today is, do we really need a full 2D perovskite, or just surface passivation can do the same work? So what we added here is a different methods. Basically, this is always the solar cell with the 3D perovskite in the middle. This is the PIN configuration. And what we wanted to do here is to passivate both the bottom surface and the top surface. So before we had just the top surface passivation, but we form clearly a 2D perovskite, and we see the formation of the 2D from XRD and from PL emission. In this case, we are using only a tiny amount of these phenylethyl ammonium cations to have a surface passivation without the formation of a net 2D perovskite layer. To do that, we invented a method to basically insert these phenylethyl ammonium cations at the bottom or at the surface of the perovskite. And then we combined both the approaches with a simultaneous bottom and top passivation. Let's look at the bottom interface first. With the bottom side functionalization, what you can clearly see is that the morphology improves. So the crystal growth of the perovskite on top of the modified interfaces is much better, which gives you increased performances. So this is the reference. This is with the 2D passivation. You see the PCE improves, which is mainly related to an improvement in the fill factor, which translates in a better interface, better contact with the bottom interface. What about the top interface? On the top interface, again, you see an improvement in the PCE, which is related to a concomitant improvement in the fill factor and in the VOC, exactly as I told you before. There is the improvement in the VOC. Why? Because the photoluminescence quantum increases, because you do have surface passivation. However, in this case, there is no sign, no indication of formation of 2D perovskites. Now we combine both with bottom and top, and you can see that we could reach very high PCE, up to 23.7%, which is the actual world record for PIN solar cells, due to the concomitant improvement of both fill factor and VOC. Again, you see the PL increases, and also, very importantly, the stability is very, very good with this kind of architecture. So, interface engineering with 2D cations is critical. It needs a lot of attention on a simultaneous control on the interface structure, but with this method, you can reduce the interface recombination and improve device VOC fill factor along with the device stability, which is very crucial. And now I would like to move a little bit out of solar cells, and I would like to show you in my last few minutes an example of exploiting this class of 2D perovskites, which are extremely fascinating class of materials because they are extremely tunable, not only for solar cells, but also for other applications like light-emitting devices. So in this case, we have a pure 2D perovskite, so not 3D anymore, and we wanted to manipulate the structure by halide compositional engineering. So basically what we used are these thiophene-based cations, and then here on the green spot, we change from iodine, bromide, and chloride. And we basically engineered the halide composition. In particular, this example is very interesting because when you, what we observe is that when you make a combination of bromide and iodine or chlorine and bromide, you do see a smooth transition of the band gap. You see that there is a red-blue shift, so basically this is consistent, this is a linear shift consistent with the incorporation of bromide and iodide in the crystal structure. But this does not happen when you mix iodine and chlorine together. It seems that you have two phases, no? A high band gap phase and a low band gap phase. Why? basically because the radius of the halide play an important role. The iodine and chloride are so different in radius that you cannot incorporate the chloride inside, and that's why you do have, in this case, two separate phases. In other words, you can, by controlling the halide composition, control the phase segregation in your material. As a result, we do have a material with a lot of phase segregation, with iodine-rich region and chloride-rich regions. Why is this interesting? This material is interesting because it absorbs mainly in the UV region. So basically this film, which is rich with chloride, is transparent to the human eye. However, it emits in the green. So you can create a palette of color for tunable emission. And this is possible because there is an energy transfer from the chlorine-rich region to the iodine-rich region. So basically at the end, you have emission only from the iodine-rich spots in your material. So with this, you can control not only the nanoscale segregation, but also control the emission, which is very interesting and promises for the formation of transparent but green light emitters for transparent LED and screen applications. So with this talk, I hope I show you a little bit the potential of these 2D perovskites for solar cells, but also for LED, and really the power of this class of materials. So let me thank all my team and you for your kind attention.
Thank you, Professor Giulia, for such an enlightening talk. And the slides were so clean and neat. Thank you.
I am happy.
Now the session is open for question and answers.
Well, if you have questions, you can always send me an email, even after, if you want.
Okay. Hello, ma'am.
Yeah.
Hi. Yeah, I had a question that we are using lead, right? So lead is quite toxic.
Yeah.
It has been known. So are there any substitute, I have read about tin, but it is susceptible to oxidation. So is there any progress in that way so that we can eliminate lead?
Yeah, that's a very good question. Is there any progress? Well, of course, research is going towards tin, lead-free materials, but they are not that efficient as lead. That's the problem. So, of course, lead is toxic. That's the other problem. Either we go towards lead-free materials, or you encapsulate your device in a way that you prevent the leakage of lead out of your device, in case, for instance, your solar cell breaks. There are two approaches, I would say.
Okay, but it can be cost effective, right? It will not increase the cost of production if you encapsulate it?
No, because in any case, you do have to encapsulate your cell. I mean, look also at silicon solar cell. You always need a glass encapsulation. So it increases the cost, that's true, but is there anyway, with lead or without lead? So.
Okay, thank you so much.
Thank you. It's not an easy answer.
Hello.
Hello.
Yes, I had one question regarding the chemical. I have seen in literature that XPS is the method which is usually used to determine the chemical bond between any interface layer and the perovskite layer. So any other method can be used to find the chemical bonding between it?
Oh, yes, you can use NMR, for instance. mass spectrometer as well, EDX, for the definition of the elements. But XPS is very much used also to determine the energy levels, Fermi levels, so then you can derive conduction band and valence band of your material. This is very interesting, I think.
Thank you.
Any more questions? Okay, I have a question from my side. Okay, there is one question in the chat box.
Yeah, have you looked into graphene-based solar cells? Oh, that's very important. No, it's not my core business, I would say, but you can use graphene on top of perovskites to improve the charge extraction. That can be done, and there are a few examples of very efficient cells with that. I hope I answered.
Okay, I have a question. When we prepare 2D perovskite and so
I couldn't hear you. Hello? Is anyone there? Hello?
Yes, it's just a connectivity issue.
Ah, okay, so it's her, it's not me. Okay, thank you. I think we lost the connection. Okay, so do you have any other questions? Okay, so
We'll
hello?
wait for 1 minute, ma'am.
Yeah.
I think Miss Dr. Anjani have lost the connection. So if there are no more questions, hello? Are there any questions?
Okay, so thank you very much for listening, and well,
Welcome.
whatever, if you have any questions, just feel free to drop me an email. Okay?
Okay.
Dr. Diptesh, I think there is one question in the chat box by Abdul Sheikh.
It is
Ma'am,
already answered.
yeah, okay.
It is
I
already
already
been answered.
answered, yeah.
Okay.
Okay, so thank you very much.
Okay, on behalf of School of Chemical Sciences and 2D-SAGE webinar committee, I, Dr. Diptesh Naik, would like to extend a very hearty vote of thanks to our today's resource person, Professor Giulia Grancini from University of Pavia, Italy, who spared a time from her busy schedule to illuminate us with a very interesting and informative talk on hybrid perovskite for solar cells. Okay, so we are really
Thank you very much. No, the honor was mine. So thank you very much for your kind invitation. I wish you a nice day, and
Thank you, ma'am.
don't hesitate to write me if you have questions.
Yes,
Bye.
sure,
Bye.
ma'am.
Bye.
Thank you all.